speaker of the session, JB Manchak.
Thanks. It is such an honor to be here today. I think that goes without saying. Over the past 10 years or so, I've been chipping away at a number of questions inspired by a question posed by Howard Stein. And this was in his 1970 paper on Gödel spacetime. Here's the question. Consider either an arbitrary given cosmological model or a model having the structure of one of the sorts assumed to hold in the real world. Then is it A, ever, B, always possible to introduce into such a model a continuous deformation of the structure leading through intermediate stages, all compatible with Einstein's theory, to a state in which Gödel-type relationships occur? Of course, there are a number of ways to interpret this question. Some have interpreted it to be a question about time machines, and a framework for investigating questions about time machines has been developed by John Ehrman, Chris Smink, who just spoke, Chris Gutrick, a few others. And I am going to be working within this framework today. My hope is to give a sense of where things stand in 2017, and also I hope to articulate a few possible avenues for future work. My thesis is threefold. There is a sense in which there are time machines in general relativity. Second, there are whole machines as well. And then third, I will conclude that, at least so far, it seems the whole machine advocate is in a better position than the time machine advocate. I will try very hard to make clear the content of these three statements. Regarding the third claim, let me just suggest at this stage that we refer to the time machine advocate as Tim and the whole machine advocate as Hal to make things a little bit easier. These are just idealized philosophers of physics trying to make the case as best they can for the possibility of building their respective machines. We'll have more to say about Tim and Hal and the tension between them toward the end of the talk. Before we begin, however, I'd like to review some basic elements of general relativity. So, general relativity determines a class of cosmological models, or spacetimes, and each model represents a physically possible world which is compatible with the theory. We take such a model to be an ordered pair MG. Now, the manifold M captures the shape, or the topology of the universe, and each point in M represents a possible event. A number of two-dimensional manifolds are familiar to us. We have the plane, we have the sphere, torus, and the cylinder will be especially important later on. Note too that any manifold with a topologically closed set of points removed also counts as a manifold. So for example, the sphere with the North Pole removed is a manifold. Manifolds are great for representing events in space-time, but we need more structure to represent how these events are related to one another. So it's the metric G that allows us to specify this extra structure. One of the jobs of the metric is to assign a double cone structure to each point in the manifold. So here we see the plane with some of the cones depicted. Notice that the cone structure may vary from point to point. Some are more narrow than others. Some are more tilted than others. We only require that the cone structure vary in a smooth way. Here's Minkowski spacetime. It's the spacetime of special relativity. And in 2 dimensions, it's just the plane and a metric which does not change from point to point. And we'll refer to Minkowski spacetime again and again in what follows. Of course, the cones have an intuitive physical significance. So it seems as though nothing can travel faster than light. And so there's an upper bound to the speeds with which particles may travel. And if we think of velocity vectors at a point as velocity vectors, then the cone demarcates that upper bound. So here we see one of the cones. This one's in 3 dimensions. Massive particles must always have velocity vectors lying inside the cone. We call such vectors time-like. Photons, on the other hand, must have velocity vectors lying on the boundary of the cone. We'll call such vectors null. And vectors lying outside the cone are called spacelike. Now, every cone has 2 lobes. And in our discussion today, we're going to limit things just a little bit. We're going to assume that ranging over the entire manifold, we can label these 2 lobes as past and future in a way that involves no discontinuity. And such spacetimes are called time-oriented. So here we see a spacetime with a Mobius strip as its underlying manifold, and this spacetime is not time-oriented. Okay, let's take a moment to review some definitions concerning curves. So, a curve is time-like on the manifold if all of its tangent vectors are time-like. And intuitively, a time-like curve threads the cones at the points through which it passes. Similarly, we could define a null curve, and we could define space-like curves. And we'll say for today that a causal curve is just one which is either time-like or null. A causal curve is future-directed if all of its tangent vectors point in the future direction. A future-directed time-like curve represents the possible life history of a massive particle. So let's use this idea of a future-directed time-like curve, or causal curve, to define the time-like past of a point. So consider a space-time and fix any point P in that space-time. A time-like past of P is the set of all points Q, such that there exists a future-directed time-like curve from Q to P. So a point gets to be in the time-like past of P if it's possible for a massive particle to travel from that point to P. So here we see the distinctive shape of a time-like past in Minkowski spacetime. The dotted lines indicate that the region is topologically open. Similarly, we can define the causal past of a point. Here we see the causal past of a point in Minkowski spacetime. And time-like and causal futures are defined analogously. Now, an interesting feature of general relativity is that it permits closed time-like curves, which allow for a type of time travel. So a future-directed time-like curve is closed if it intersects itself. Here's an example. Here we see Minkowski spacetime, which has been rolled up along the time direction. A future-directed time-like curve is shown and it intersects itself. It's possible to travel from an event on the curve in the future direction and get back to the same point. We say that a spacetime is chronological if it has no closed time-like curves. Okay, let's move to surfaces just for a moment. We'll say that a surface is space-like if every curve within the surface is a space-like curve. A set is achronal if it's not intersected more than once by any time-like curve. So here we see an achronal space-like surface in Minkowski spacetime. A surface is a slice if it's space-like, achronal, closed, and without any edges. So here's a slice in Minkowski spacetime. Now consider an arbitrary set S on a spacetime manifold. The domain of dependence of S is the set consisting of those points Q such that every causal curve through Q without endpoint intersects S. So there's a sense in which if it is indeed the case that nothing can travel faster than light, then there's a sense in which conditions on S can be used to determine the physical situation on all of D of S. And there are a number of theorems speaking to that idea. So here we see the domain of dependence of a space-like achronal surface in Minkowski spacetime. Note the distinctive diamond shape. A spacetime which has a slice such that the domain of dependence of that slice is the whole manifold is called globally hyperbolic. So this means that information on S will determine the physical situation on all of the spacetime. So Minkowski spacetime shown here is globally hyperbolic. Any causal curve without endpoint must intersect this slice somewhere. So the domain of dependence is the entire manifold. But if we remove a point from this spacetime, just one point, the resulting spacetime is no longer globally hyperbolic. So a causal curve without any endpoints is shown here, and note that, of course, it doesn't reach the slice because it finds that hole. So globally hyperbolic spacetimes are causally well behaved. Indeed, it's a basic result that all such spacetimes are chronological. The final portion of definitions will consider extensions in spacetime. So a spacetime is an extension of some other spacetime if the second can be properly embedded into the first while preserving the metric structure. So here we see two spacetimes. The first is just a truncated version of the second, and so by construction, the second is an extension of the first. A spacetime which has no extension we'll call maximal, and otherwise we'll call it extendable. So with the use of Zorn's lemma, you can prove this fundamental theorem. Any spacetime which is not maximal has a maximal extension. Finally, we'll say that a spacetime is past maximal if it has no extension in the past direction. So, for example, here we have the bottom half of Minkowski spacetime. It is not maximal, but it is past maximal. Okay. Now we're ready to talk about time machines. So how does one characterize this notion within general relativity? Let's start by considering an extendable, past maximal, globally hyperbolic spacetime. We might think of these models as having, in the language of Stein, the structure assumed to hold in the real world so far. And let us say that such spacetimes are starters. So every machine needs a starter, right? So here's our starter. Now, let's consider a definition, a naive definition of a time machine. So let's say that a starter is a naive time machine if all of its extensions fail to be chronological. So the intuition behind the definition is straightforward. Here the starter represents a physically reasonable universe before the machine produces the closed timeline curves. The requirement that all of its extensions fail to be chronological is supposed to capture the idea that the future universe is forced into allowing for time travel. So consider Misner spacetime. So here, the manifold is cylindrical, and the metric structure is such that the light cones tip over as they move up the cylinder. So there are no closed time-like curves in the bottom half, and in the top half there are closed time-like curves through every point. So the region below the dotted line, the bottom half, taken as a space-time in its own right, is not maximal, but it is past maximal, and it is globally hyperbolic. And so it counts as a starter. Question: is this starter also a naive time machine? So in other words, does every extension of this space-time contain closed time-like curves? And the answer is no. Right? So here's an example space-time which is chronological. We take Misner space-time and we cut a hole in the top half, and we do it in such a way that prohibits these closed time-like curves from forming. So the bottom half of Misner space-time is not a naive time machine. And in fact, there's a no-go result by the Russian physicist Sergei Krasnikov, which shows that no space-time is a naive time machine. So we're going to need to move past this definition if we want to consider such space-times. Here's a suggestion by John Ehrman and others. A starter is a P time machine if it has an extension with property P, and every extension with P fails to be chronological. So here, property P is used to pare down the space of starter extensions to those which are physically reasonable in some sense. We need to add condition 1 to the definition to avoid a nuisance case. We don't want to count a starter as a P time machine simply because condition 2 is vacuously true. So now let's consider some candidate properties P. Recall that what seemed to keep the bottom half of Misner spacetime from being a naive time machine was the existence of an extension which had a hole of sorts, which prevented the closed time-like curves from forming. One wonders if there's a condition to rule out the hole in the example. And there certainly is such a condition. For some time now, hole freeness has been used to rule out such spacetimes. So here's the precise formulation. A spacetime mg is hole free if for every space-like surface S in M, no metric preserving embedding will be such that the domain of dependence under the embedding is a proper subset of the domain of dependence of the surface S under the embedding. The idea here is beautifully simple. We just require that the domain of dependence be as large as it can be. So, for example, take Minkowski spacetime with one point removed from the manifold. Note that the domain of dependence in this mutilated spacetime is not as large as it could be if this point weren't removed. It's not the full diamond shape, if you were. So the spacetime is not hole free. It's been suggested by some experts that only whole-free spacetime should be taken seriously. So here is Bob Garrosh on the matter. One might now modify general relativity as follows. The new theory is to be general relativity, but with the additional condition that only whole-free spacetimes are permitted. So other physicists such as Ellis and Schmidt and Clark have taken similar approaches. Okay, well now we have all the resources to formulate a rather precise question, right? So if P is the condition of whole freeness, are there P time machines? This was the central question asked by Ehrman, Smink, and Vutric back in 2009. But 2009 was a simpler time for a lot of reasons. With respect to whole freeness, things were about to get quite strange. So a bit of backstory on this condition. So in his paper on whole freeness, Garrosh claimed, without any proof, that Minkowski spacetime is whole free. A few months later, Ellis and Schmidt claimed, again without proof, that every maximal globally hyperbolic spacetime is whole free. And a proof eventually surfaced in 1993 by Chris Clark. Thus, it seemed that a large class of interesting and arguably physically reasonable spacetimes did not have holes. So, what happened? Okay. It turns out that I was able to show that the claim of Ellis and Schmidt was actually false. So Clark's proof contained some errors there. There are many maximal and globally hyperbolic spacetimes which have holes. And so, right after I published this paper, Sergei Krasnikov read it. He doesn't like time machines, by the way. So he wanted to even strengthen this result, and he showed that Minkowski spacetime itself has holes. So the spacetime of special relativity has holes under this Garrosh definition. There's a lesson. If you ever claim anything, you should probably prove it in a paper. Maybe. That's just a suggestion. Anyway,
Good philosophers have a problem.
Okay, so why is this true? Minkowski spacetime has holes. Okay, consider a space-like surface here without boundary. There are a number of examples that show this. This is the simplest one. Its associated domain of dependence is this open region here. It's an open set. But we can embed it into a rolled up Minkowski spacetime in this way, so that now some of the boundary that wasn't there before now is. So it's gotten a little bit bigger. Part of the boundary is now included where it wasn't before. So the upshot is that the property of whole freeness, at least as it's formulated by Garrosh, is not physically reasonable. Where does this leave the situation with time machines? Well, first, there are a number of ways of fixing things up. I worked with Bob on doing that in one of my papers. But there are a whole bunch of whole freeness conditions. But there is a property I want to focus on for the remainder of today. And to do so, let's review some basic facts about time-like and causal pasts and futures. So, okay, let's look at time-like pasts first. Time-like pasts are always open in any space-time, and given any point in that space-time, the time-like past to that point will always be an open set. And causal paths are sometimes closed. So, for example, in Minkowski space-time, this causal path is closed. But sometimes they're not closed. So here is a space-time. I've removed a point on the boundary here, and now this causal path is neither open nor closed. So this suggests a new, very simple kind of hole freeness property. So let's just say that a space-time is J hole free if for all P and M, the causal past and future of P is closed. As Stephen Hawking once remarked, this property can put limits on the kinds of gaps that space-time can have. Is it more physically reasonable than hole freeness? Well, first, recall that the downfall of hole freeness was that it wasn't satisfied by Minkowski space-time. But we know that all globally hyperbolic spacetimes, including Minkowski space-time, whether or not they're maximal, they will all be J-hole free. So the upshot is that J-wholeness, whatever else is the case, it's more physically reasonable than hole freeness. Now, recall our working time machine definition from Ehrman and others. A starter is a P time machine if it has an extension with property P, and every extension with P fails to be chronological. One precise question is, well, now if we plug in J hole freeness for P, do we get a P time machine? And the answer to that is yes, we do. So let me say something about the proof. Consider Misner spacetime again. First, note that it is J-hole free. So all we must do now is show that every extension to the bottom half of this spacetime, which doesn't have J-holes, fails to be chronological. To help us do this, let's note that there are two types of extensions which may help to clarify things. There are those extensions which contain all of the points in the boundary region between the top and bottom halves of Misner spacetime, the dotted line here. So Misner itself is one such extension. And there are other extensions which do not contain all of the points in that boundary region. So here's one. So the first stage of the proof is just to show that every extension which contains all of the points in the boundary region must contain closed time-like curves. And then the second stage is to show that every extension which does not contain all of the points in the boundary must have J-holes. So here we see an example which does not include all of the boundary region, and we see that the time-like past of the indicated point is the bottom half of the spacetime. Clearly it has a J-hole since the causal past of the point marked does not contain all of its boundary points. So the part it doesn't contain is the dotted line. So together the two lemmas give us the result that we want. Well, let's take a step back here. What should we make of the time machine existence result just mentioned? Consider again the bottom half of Misner spacetime. We know that some of its extensions are chronological, and it's a fairly benign assumption to assume that all physically reasonable spacetimes are chronological. So I'm wondering then, why we can't, here's one. Why we can't think of the bottom half of Misner spacetime as a type of hole machine. So consider the following quite general machine definition. We say a starter is a PQ machine if it has an extension with property P, and every extension with P has Q. So as before, property P is used to pare down the space of starter extensions to those which are physically reasonable in some sense. And property Q is the one intended to be produced by the machine. So I've just argued that there is a PQ machine where P is J-hole freeness and Q is the failure of chronology, but also switched. So there's a PQ machine where P is chronology and Q is the failure of J-hole freeness. So which is it? Is the bottom half of Misner spacetime a type of time machine, or is it a type of hole machine? One way to break the stalemate is to investigate how robust the results are with respect to different choices of the background class of physically reasonable spacetimes. And this turns out to be quite a project, and here's essentially why that is. Suppose for some properties P and Q you find a PQ machine. And suppose there are properties P0 and P1 around such that P0 implies P, which implies P1. It does not follow that there is a P0 Q machine. It does not follow that there is a P1 Q machine. So the former is not guaranteed since P0 may be so strong that the starter used to exhibit the PQ machine doesn't have any physically reasonable spacetimes. Remember, we have an existence clause in the definition. We need at least one physically reasonable extension. And if P0 is strong enough, we won't get that. On the other hand, the latter is not guaranteed either, since if the class of physically reasonable spacetimes is enlarged by P1, then it's possible that the starter used to exhibit the PQ machine may be such that one of its P1 but not P extensions is also not Q. So one has to check for existence results one at a time, as it were. Kind of. So, how robust are the time machine and hole machine results mentioned in the previous section? To aid our presentation a little bit, consider these property abbreviations. We've already talked about the first three of these conditions. The final one, that of being a vacuum solution of Einstein's equation, guarantees that we have a nice local metric structure. So in particular, if V is satisfied, so are all of the so-called energy conditions which place constraints on the distribution and flow of matter. So let's now investigate the robustness of the time machine result. So here's the very best I can do. It's not much. But we know that Misner spacetime is one extension to the bottom half of Misner spacetime. And we know that Misner spacetime, even its four-dimensional counterpart, is J and M and V. So, it follows that there's a PQ machine where Q is the failure of chronology, and P is implied by J and M and V and implies J. So here's a picture to help see what's going on. So the entire space represents the class of all spacetimes, and the dotted lines represent possible subclasses P of physically reasonable spacetimes. As long as P is smaller than J, but larger than J and M and V, an existence result goes through. Outside of that, all bets are off. I don't know. Okay, what about the hole machine result? How robust is it? Let's once again return to Misner spacetime. Let's remove a point from the boundary region between the top and bottom halves. And now we can multiply the metric by a smooth conformal factor that's represented here by this color gradient, which approaches 0 as this missing point is approached. The light cone structure remains perfectly unchanged. In particular, it is still the case that the bottom half of this spacetime is a starter. But I claim that any extension to this starter will have J holes. So to see this, note that because of the smoothness considerations we have, any extension will fail to have the missing point. And as before, you can show that any extension which fails to have all of the dotted line will have J holes. Moreover, I claim that one can find an extension which is maximal and chronological. So here's one. You start by considering the top half of Misner, and then you cut a vertical slit as shown, and then you multiply the metric by a conformal factor which matches smoothly with the bottom, but also approaches 0 as you approach the slit. The result is a chronological maximal extension. So the upshot of all this is the following result. There is a PQ machine where Q is a J hole, and P is any property which is implied by C and M. So as before, let's take a look at a picture. The entire space represents all spacetimes. The dotted lines represent possible subclasses P of physically reasonable spacetimes. As long as P is larger than the set of C and M spacetimes, the existence result will go through. Notice that unlike the time machine case, there's no outer boundary to constrain P here. In other words, P could be some universal property like being a spacetime or being an extension or something, and the result would go through. If you like, we have here a naive hole machine. So it seems we have a clear sense in which Hal, our hole machine advocate, is in a better position than Tim, our time machine advocate. But wait, Tim says. Wait. That conformal factor that you used to construct that model will likely make any starter extension physically unreasonable in the sense that its local metric structure will be badly misbehaved. In particular, the energy conditions won't be satisfied. Okay, good point, Tim. Hal has another trick up his sleeve. So here it is. Consider one final time the bottom half of Misner spacetime. We know that any chronological extension to this starter has J holes. How nice can we make one of its chronological extensions, I wonder? Well, pretty nice, it turns out. So let's consider an infinite number of copies of Misner spacetime, indexed by the integers, and cut a vertical slit in each of them, like so. Now label the left and right slits, like I've done here, and finally for each integer n, identify the slit ln with the slit rn plus 1. So the left slit in spacetime 0 is identified with the right slit in spacetime 1. The left slit in spacetime 1 is identified with the right slit in spacetime 2, and so on in the other direction as well. The result is a maximal, chronological, but also a vacuum solution. So aside from having holes, which were produced by the machine, one could think, the spacetime is about as nice as one could command. It follows that there is a PQ machine where Q is the failure of J hole freeness, and P is implied by C and M and V and implies C. So back to the picture. As long as P is bigger than C and M and V but smaller than C, we get an existence result. Outside of that, all bets are off. Okay, so where are we at? First, I claim that we do not know what the class of physically reasonable spacetimes is. Maybe that's controversial, I don't know. I've argued in a number of places that we can never know such a thing. But the way I see it, Hal has the upper hand here. Because if you'll allow me a poker metaphor, it seems like there are just more outs for Hal as compared with Tim. So we have 3 existence results on the table. If the class of physically reasonable spacetimes is relatively small, then both Hal and Tim are in a good position, I think. Tim has result 1. Hal has result 2. Note the lovely symmetry of these 2 results. So in this scenario, where the class of physically reasonable spacetimes is small, I think their hands are roughly equal in strength. But if the class of physically reasonable spacetimes is rather large, then Hal has result 3 as a sort of ace in the hole. So you may do the accounting differently, and that's fine. The main point I want to emphasize at this stage is that there is plenty of work to do. So here are 2 avenues for future work that may help to clarify matters concerning time machines and Hall machines. Okay, here's the first. Suppose one had an additional condition, call it U, which could be used to further restrict the class of physically reasonable spacetimes. So perhaps the so-called generic condition used in the standard singularity theorems is one such. Then a few questions present themselves. I've listed them here. And Tim could hope for an affirmative answer to the first, and then negative answers for the rest. Hal could hope for things to go the other way. But because we have such freedom here with what we can choose for you, there are lots and lots of open questions. Another avenue would be to consider other hole freeness properties besides J-hole freeness. So there are several other conditions already on the table, and there are more that one could introduce. One wonders if the fortunes of Tim and Hal remain consistent over explorations of these other conditions. This is almost entirely uncharted territory. There are literally dozens and probably hundreds of open questions, just considering the small handful of hole freeness conditions on the table. It's a rather large research project. My hope is that maybe some of the youngsters in the audience here today will be inspired to tackle some of these questions. I was hoping Howard was in the room so I could sort of point at him and challenge him to kind of finish some work that he started. But I'll have to talk to him about that some other time. Anyway, thank you so much.